Bismillahirrahmanirrahim. This video is about ideal transformer. Okay, now a couple of slides will discuss some theoretical part. The first one is what is an ideal transformer. An ideal transformer may be thought of a first order approximation model of an iron core transformer. Now this is a transformer and this is the core, which is made of very fine strips. So several strips that make the core, and these strips are made of iron material. And in diagram, this is represented by these two vertical bars. So whenever there is a vertical bar, that means it is iron core, and when the vertical bars are absent, that means it is paper core or air core. And then the turns of the primary and secondary are represented by numbers N1 and N2. And from equation 20, we learned that L2 over L1 is the N2 square over N1 square is equal to A2 square. So I will not go into the details of this. You can check from the book. And so from here we can conclude that A is N2 over N1, and this is called the turn ratio. One more thing is called the coupling coefficient K. Now, coupling means, like here you have the primary turns and secondary turns, they're overlapping, and in this case the primary turns and secondary turns are not overlapping, they are away. So it is the constant K actually indicates how much they are coupling with each other, and so its value could be from 0 to 1. So 0% coupling or 100% coupling. And since this here has indicated that K is equal to 1, that means there is a perfect coupling, 100% coupling, or this is also called tight coupling. And then we'll come across this formula. This is also again derived in your book. What it says is that the mutual inductance has to be less than the under root of the two inductances multiple. So the mutual inductance cannot be greater than the geometric mean of the self-inductance of the coil. So it has to be less. And so to equate it, we can take a constant K. This K is actually the coefficient of coupling that we discussed here. So M can be replaced by K under root L1 over L2. Now this was in time domain. You can write it in phasor domain or frequency domain by just replacing these two, j omega L1 and j omega L2, and M as j omega M. And then we can write the to write the voltages, we have to also take into account the mutual voltages. So this voltage caused by the current I2, and this voltage caused by current I1, and the signs we have discussed already in the previous video. So if you can't follow this, you just go and have a look at the previous video. But again, just for information, this current I is touching the coil or entering the coil. Therefore, this has to be positive sign at the top. So positive sign at the top and negative at the bottom. And similarly, I2 is touching the non-dotted terminal. Therefore, non-dotted terminal will be positive and the top will be negative. So that is how we write. So let's now go and write the voltage equations. By KVL, this voltage V1 is the j omega L1 times I and minus this voltage. So j omega L1 times I minus j omega Mi2. And similarly here we can start from one corner. So j omega minus j omega M I1 minus j omega M I1 and plus j omega L2 I2 and plus ZL I2. So we have combined these two, taking I2 common. So this is the second equation, or equation for the right hand side. And then from here we can solve for I2. This one goes to the left, and then we get the value of I2 and put that value here, and therefore equation 22 will become something like this. And we know that the input impedance is V1 over I1. So impedance here is V1 over I1. And from here, therefore, if we take I1 common and divide it on the left hand side, then what is left is this term. So this is the Zin, or the input impedance, looking at this terminal. And now we have discussed that M should be equal to K under root L1, L2, and also we have mentioned that K is equal to 1. So putting that, we get M square is equal to L1 and L2. So we put that value now here for M. This is the value. And also from this formula we can put the value of L2 is A square L1. L2 is A square L1, and this. So this is the new term that we get. Okay, so we were here. Now we take the LCM, multiply, and these two terms get cancelled. So this is what remains. And again, if we divide by j omega L1, then this becomes here, this becomes A square, and top becomes ZL. And now there is an assumption. Besides unity coupling coefficient, another characteristics of the ideal transformer is an extremely large impedance for both the primary and the secondary coils. So this suggests that L1 and L2 tend to be infinity, or very large. And so in this, if we assume L1 to be very large or tending to infinity, therefore this term will become 0, and so Zn will be equal to ZL over A square. So this is a very, very important derivation. This Zn is equal to ZL over A square means the first important characteristics of the ideal transformer is therefore the ability to change the magnitude of the impedance or to change the impedance level. So whatever was the value of the impedance here at the primary side, it will be divided by, or it will appear very small because it is being divided by the number of turns square. So here is an example. The ideal transformer having 100 primary turns and 10,000 secondary turns, so 100 turns here and 10,000 here. Therefore, they will have a turn ratio of 100. That means A is 100. So any impedance placed at the secondary terminal will appear in the primary terminals reduced by 100 square, because we are dividing by A square, or by 10,000. So if we had an 20,000 ohms resistor here connected, then that will appear to be 2 ohms in the primary. So you can see how much is the reduction. Similarly, if we have 200 milliamp Henry inductor here, this will appear here as 20 microhenry, and same for capacitor. 100 picofarad capacitor looks like 1 microfarad. Now we'll see a couple of uses of transformers. The first use is for impedance matching, and the concept is actually that a speaker that we see in radios generally has an impedance of 8 ohms, whereas the circuit prior to this has a high impedance, like here it is 400 ohms. So to match the two, we got to use a matching transformer. And what is the effect of this? You can see that the impedance on the primary side is 400 ZG, or we can say Z input here, and we know that this is equal to ZL over A square, 8 over A square, and so from here we can see that A is 1 over 22.4. That means N1 over N2, which is 1 over A, is 22.4. So if we have a transformer of this turn ratio, then we can match the output with the input. Now the transformer can also be used as for current adjustment, and let's see how it is done. If we take the voltage loop, this loop, and write KVL, we'll get this equation. We got this early, and from here we can find the value of I2 over Im, which will become j omega m divided by this term. And now we are assuming that L2 is very high, almost infinite. Therefore, this term will become equal to j omega L2. This will become negligible as compared to the value of L2. So we'll write I2 over I1 as j omega m, and here we'll just write j omega L2. Now we cancel j omega, so it becomes m over L2, and we have learned earlier that m is equal to under root L1 L2 when k is equal to 1, which is 1 here, and so we get this term, and then by simplifying we get it to be under root L1 over L2. So this is the value of I1. Now in terms of n, we know that L2 L1 is related by N2 N1 by this formula. So from here we can write I2 over I1 is equal to 1 over A, because L2 over L1 will be just A. Under root L2 over L1 will be just A, and when you invert this to get L1 over L2, then it will become 1 over A. So L1 over L2 will become 1 over A. So I2 over I1 will actually become 1 over A. And again from here 1 over A will be, N1 will go up and N2 will come down, so it will be N1 over N2. And so from here you can see that I2 is N1 over N2 multiplied by I. So if you want to get the increased value of I2, then you have to increase the primary winding, number of turns in the primary winding, or reduce the number of turns in the secondary winding. So this is how you can get the adjustment in the value of output current. Now let's see how a transformer can also be used for voltage level adjustment. Now from this diagram you can see that V2 is I2 into ZL, I2 into ZL. We also have V1 is equal to I1 into Z input here, so Z input. And we learned earlier that Z input is equal to ZL over A square. So we put that value for Z in, so it will become like this. And now we divide V2 by V1. So this term divided by this, and cancelling ZL, so we get I square I2 over I1. And we earlier learned that I2 over I1 is 1 over A. So this is can be replaced by 1 over A. So here we replaced I2 over I1 by 1 over A, which cancels and becomes A, and we have learned from here that A is equal to N2 over N1, so we write N2 over N1, and therefore our equation becomes that V2 over V1 is equal to N2 over N1. Now if you compare this with the current relation, this is directly proportional, that is, as if you increase N2, then V2 will increase. If you decrease, so this is direct relation, but in case of a current it is opposite. If you increase N2, then the current I2 will decrease. Okay, anyway, now we had this for the current, so if we reverse to bring N2 on the top and N1 at the bottom, then the relation will become I1 over I2. So now we replace this N2 over N1 by I1 over I2. So our relation will become V2 over V1 is equal to I1 over I2, and by cross multiplying we can see that V2 I2 is equal to V1 I1. And if you note carefully, this is actually the power. So power input or power on the primary side is equal to power on the secondary side. So although the current and voltages can be changed by the transformer, but the power on both sides, that is on the primary side and on the secondary side, will remain same. No power can be generated. Okay, now let's solve or discuss the solved example. For the circuit given in figure, determine the average power dissipated in the 10 kilo ohm resistor. So the power dissipated here. So straight away we reflect this and bring it to the primary side, and we know the formula that Zn is equal to ZL over A square. So in this case, this is the same example that we did earlier, that the turn ratio is 1:10, that means A is 10. So A square will become 10 square, and ZL is 10K. So 10K divided by 100 will give 100. So let's see it here. The power dissipated is obviously I square into R. So this is R, so I square into R. But then we have to know how much is I2. And for that, we take help of the circuit, ZL over A square, ZL over A square, and I was mentioning ZL is 10K or 10,000 divided by A is 10 square, so 10 square. And if you solve, we'll get the value of this term as 100. So Zn is actually 100 ohms. And now we can find the current I1. This voltage divided by total resistance. Voltage divided by total resistance is 250 milliampere is the I1 current. And now we use this relation to find I2. So I2 is 1 over A I1, 1 over A is 1 over 10, and I1 is 250, so I2 is 25 milliamperes. And so now power, we just plug in the value of I2 here. So power is 6.25 watt. Okay, now the practice problem. It says repeat example 13.7 using voltages to compute the dissipated power. So instead of current, we'll use voltage to calculate the power. It's the same circuit. So now the power equation, we can write it as V square over R. So here this is R and this is V2. So V2 square over R. So we need to find V2 now. and V1. So this is again same way, we got the equivalent circuit and its value is 100. So we'll now look at this circuit and we need to find V1, so we do it by voltage division rule. Total voltage divided by total resistance multiplied by this resistance. So V1 is 25 volt. And now we take the transformer relation. This V2 over V1 is N2 over N1. We don't know N2 and N1, but we know A. So we just plug in here. N2 over N1 is actually A. So it is A over 1. And V1 is 25. So V2 is 250 volt. So I hope this gives you an understanding as to how to solve this type of problem. Thank you. Okay, sorry, I got the voltage. We need to find the power, so just plug in this voltage, and the power in this case also is 6.25 watt, the same power. Thank you.